Hello everyone and welcome back to unit number 4, and we are going to explore the practical real world of drone technology. As the title of the slide indicates, our focus will be on commercial application and regulatory compliance. This means we'll be looking at two interconnected themes. First, we'll examine the incredible ways drone are being used in various industries to innovate, improve efficiency, and create new services. Second, we second and just and importantly, will dwell into the rules, laws, and ethical guidelines that governs the use of this powerful technology. Understanding both of this aspect is absolutely essential for everyone looking into work professionally in this field. As we can see from the overview of the slide, we will cover a lot of ground. We'll begin with the fundamental topic of selecting the right drone for specific application. The drone uh, you will be used for cinematic photography is different from one designed for agriculture spraying. So knowing how uh, to choose the right tool for the job is the first step to success. From that, we'll move on into some of the most predominant commercial sector. We'll take a closer look at agriculture, where drones are transforming how we monitor crops and manage lands, leading to what are known as the precise agriculture. We'll shift our focus to the fast evolving world of delivery service, exploring how companies are using drones to solve the last mile delivery problem and transport goods quickly. Another critical problem we'll discuss is the infrastructure inspection. Drones offer a revolutionary way to inspect bridges, power lines, wind turbine, and other large structures, which is not only more efficient but dramatically saves the traditional method. Of course, drone operators commercially isn't about flying a machine. It's about operating within a structured legal system. That is why we will dedicate a significant portion of our discussion to regulatory compliance. This involves understanding the specific rules set for aviation authority that indicates where you can fly, when you can fly, and what certificates you need. Hand in hand with this are the broader legal and ethical consideration. We'll discuss important topics like privacy, data protection, and public perception of drones. All of these shapes the license, social license from this technology to operate. As with these commercial ventures, risk management is a key, which brings us to the topic of insurance. We'll cover why insurance is often a legal requirement and always a business necessity for commercial drone operators. Finally, trying all these topics together is an unwavering commitment to safety. We will conduct by focusing on core safety guidelines that every responsible pilot and organization must adhere to. The safety is the bedrock of entire aviation industry, and drone world is no exception. This unit is designed to provide you with holistic view, connecting the exciting possibility of drone technology with the practical readiness of operating safety and legality in the modern world. Now that we have set the stage, let's discuss the fundamental question. Why are drones or UAVs so important in the business world today? What is their commercial relevance? Image on the side provides a fascinating real-world example. We see a construction profession on a busy work site using a drone to get a closer, clearer overhead view of the project. This isn't seen from the future, it's happening every day on the job site around the world. This single picture perfectly encapsulates the core value proposition of commercial drone. They also allow us to work smarter, gather much information and safety and increase the safety. This is a practical reality of how this technology is transforming industry. The text on the slide highlights the UAV and becoming increasingly vital across a number of key fields. Many people associate drone with their military origins, where they are used for intelligence, surveillance, and reconnaissance mission to reduce the risk to human persons. This, their impact on the civilian world is now just a profound. In agriculture, drones are no longer novel. They are essential tool for what we call precise farming, helping to monitor crop health, optimizing irrigation, and improve yield. In the world of logistics, companies are heavily investing in drone delivery to solve the complex last mile problem, aiming to get package to consumer after a large efficient than ever before. And in the security industry, drones offer a powerful and cost-efficient way to monitor large property patrol parameters and provide aerial oversight during security operation. In all areas, UAVs have moved from being a nice to have to a need to have technology. It's also useful to think of a drone, as the slide suggests, as components of intelligence or support transport service. The drone itself is a transport mechanism, but what is transporting? What it is transporting? In many cases, it's not a physical package, but a sophisticated sensor package. This is where the intelligent part of the equation comes in. The data gathered by the sensor, whether it is high resolution imagery or the thermal data or a LiDAR scan, it is a real product. The data processed and analyzed to provide business and actionable insight or intelligence that was previously unavailable or too expensive to acquire. Because drones can be deployed quickly and economically, these intelligence services can be offered at a price point that matches them accessible to much wider range of companies and even individual consumer, democrating access to aerial data. The key driver of this accessibility has been the development of MAVs or miniature air vehicle. These smaller, often very portable drones have created an inexpensive platform for carrying powerful imagery technology. The slides mention electro-optical EO and infrared IR cameras. EO cameras are what we consider high definition, standard high definition visual camera, capable of capturing incredible detail photo and video for inspection or mapping. IR camera or thermal camera see the world in terms of heat signature. They allow them to identify issues which are invisible to the naked eyes, such as water leaks, faulty electronic components, or areas of crop stress. The capability to put these advanced sensors into the data for a fraction of cost of helicopter has been a true game changer. And this all leads to the final point. The collection of aerial data is enabling new business model and transforming traditional industry. Entire companies are now built around providing drone-based data service. Meanwhile, establishing industries like construction, energy, and insurance are fundamentally changing the workflow to incorporate the insight that this technology provides, leading to greater efficiency, enhanced safety, and better decision making. While the potential for air vehicle is immense, their widespread adaptation isn't without significant obstacle. This slide outlines the key challenges and the future direction that engineers policymaker, and the business in the field are currently navigating. These challenges can be broadly categorized into technical, economical, and regulatory hurdles, and understanding them helps frame the importance of work we are doing in this course. First, let's look at the technical challenges. This industry is in the constant push for increased reliability, extended capacities, and improved ease of use. Increased reliability is absolutely critical. For drone to be trusted with valuable payload or to operate in close proximity to people and infrastructure, they must be exceptionally dispensable. This means designing systems that are resilient to component failure, software glitches, and environmental factors like high wind or signal loss. Alongside the reliability is the demand for extended capacity. User wants drone that can fly longer, carry more sophisticated sensor, and operate with great autonomy in complex environment. This drive research into more efficient battery technology, lighter and stronger material, and more advanced artificial intelligence for navigation and decision making. Finally, for this technology to become truly uh, unique, we need improved access, ease of use. A drone shouldn't require a team of highly specialized engineers to operate. The goal is to create a system that are intuitive and can be deployed quickly and easily by professionals in various fields. Whether it is a farmer checking crop or a first responder survey a disaster area. Next, we face significant economic challenges. The core issue is the need for reducing cost while maintaining high standards for performance and safety. This is a classic engineering balancing act. The high-end sensor, processor, and the communication system that provides the best performance and the reliability are often the most expensive. As we push for mass adaptation, the price point has to come down to make the technology accessible to more industries and small businesses. However, this cost reduction cannot be at the expensive rate. We cannot compromise the quality of the component or software in the way that would endanger people or properties. Therefore, the challenge lies in the innovation, finding new manufacturing techniques, developing more efficient algorithms that can run on a less expensive hardware, and designing a system in a way that is inherently cost effective without sacrificing the quality. Perhaps the most complex barrier is the set of regulatory hurdles we face. The primary issue here is the integration of unmanned aircraft into national and international airspace. Our skies are already a crowded and meticulously managed system for manned aviation. The safely introduced the, sta- the safe, safety introduces millions of autonomous drones into the environment is an enormously undertaking task. The government and aviation authorities around the world are working to develop a new rules and new air traffic management system specifically for unmanned aircraft that are they are grappling with questions of certification, pilot licensing, operational restriction, and piracy concerns, creating a comprehensive legal and regulatory framework that ensures safety without stifling innovation is one of the most critical steps needed for the drone industry to reach its full potential. Given these broader challenges, our focus area in this unit becomes clear. We will be concentrating on the technical core of the problem, the guiding and controlling of limited payload small and miniature aircraft system. By advancing our understanding of these fundamental principles, we are directly contributing to the solution for the challenges we have just discussed. Better guidance and control algorithm lead to more reliable and capable drone. More efficient control system can reduce computational requirement, which in turn can lower cost and proven track record for safety reliability control in foundation upon which our future regulation will be built. This is the heart of engineering work that will unlock the future of MAVS. To begin solving the challenges we just discussed, we need a robust and a well thought out design. This slide presents an integrated view of typical MAV system architecture. Think of this as the blueprint of an autonomous drone, showing us how the different parts work together to create an intelligent flying machine. We'll break down this architecture into its core component. First, we have the fundamental system component. This starts with the most obvious part, the unmanned aircraft itself, which is the physical airframe. This includes the body, wings or arms, motors, propellers, and everything that makes up the physical structure. This is the hardware that actually moves through the air. The brain of this hardware is the autopilot, which is the onboard computer that executes the flight software. To understand this environment and its own status, the drone relies on a suite of sensors. These are the drone's eye, ear, and typically which includes inertial measurement unit (IMU) with accelerometer and gyroscope, a GPS for location, a barometer for altitude, and a magnetometer for heading. However, the raw data from these sensors can be noisy or inaccurate. That's where this state estimation comes in. This is a critical software module that takes all the incoming sensor data and fuse it together to produce a single accurate and reliable estimate of the drone's current state, its precision, position, orientation, and velocity. Building upon these core components are the navigational component, which handles the higher level logic of autonomous flight. The process begins with Path Planner, giving given a mission such as surveying this area or fly from point A to point B. The path planner's job is to compute a safe and an efficient route. It acts like a GPS in a car, planning the entire journey before you start. Once a path is generated, the path manager takes over. Its role in the following is to follow the path in issuing immediate tactical command like fly forward at the speed or turn to this heading. It is the component that ensures MAV stay on the route defined by the planner. Finally, these high-level commands are sent to the control system. These are low-level system that translates commands like pitch up into exact adjustment in motor speed required to make that happen, ensuring aircraft remain stable and responsive throughout the maneuver. The power of this design lies in its modular architecture. As the slide notes, each blocks interact with other, and this interaction is what enables complex autonomous behavior. The sensor provides data to state estimator, which provides the drone's current state to the path manager, which executes the plan from the path planner by sending command to the control system, which then drives the physical aircraft. It is continuous feedback loop. This modularity makes the system easier to develop, debug, and upgrade as an engineer can work on individual blocks without having to redesign the entire system. Ultimately, this brings us to the core of our unit, which the hardware is essential. Our focus will be on the design for the software algorithm that enables autonomous and self and semi-autonomous flight. This is the sophistication of this software, the state estimators, the planners, and the controller that truly defines the capacity of modern MAV. Having laid out the architecture of MAV, the next logical question is how we actually design the intelligent software that runs on it. The answer lies in our design philosophy, which is centered on the principle of modeling for control. We cannot control what we cannot describe. Therefore, our first step is always to create a mathematical representation of the drone and its environment. Our process begins by translating the physical system into a simulation. To do this, we need to create a detailed mathematical model that captures every important aspects of drone behavior. This includes modeling of its rigid body kinematics, which describes the geometry of its motion, its position, velocity, and orientation, without considering the forces involved. Next, modeling its dynamics, which is where we apply physics to understand how forces and dark causes the drone to accelerate and rotate. We must develop a model for aerodynamics, which accounts for the complex force of lift and drag generated as the drones moves through the air. Finally, we need to model the sensor themselves, capturing their characteristics, limitation, and potential for noise. The ultimate goal is to build a comprehensive simulation that acts as a digital twin, a virtual drone that behaves almost exactly like its real-world counterpart. This allows us to test our ideas safely and cost-effectively in a virtual environment. While highly detailed model is perfect for simulation, it can be too complex for designing the control algorithm themselves. This leads us to the next step, creating simplified design models for control. We develop different models for different tasks. For low-level control such as autopilot function that keeps the rod stable, we often use simplified model that accurately captures the drone's behavior during specific maneuvers like hovering. These models might ignore certain complex aerodynamic effects to make the mathematics of designing a stable feedback control more manageable. For high-level guidance system like Park Planner we discussed earlier, we can use a simpler model. For example, we might model the drone as a single point in space, ignoring its orientation entirely. Because for long-range path planning, only its position and velocity are relevant. The key is to strategically simplify reality to create a model that is just complex enough for the task at hand, but more, but no more. This entire approach is embedded within a iterative design process. It's a cycle that continuously refine our design until it meets the requirement performance and reliability. The process starts with the design phase, where we create our own guidance and control algorithm using our simplified mathematical tool. Next, we move to simulation, where we test these algorithms extensively on our high fidelity digital twin to see how they perform under wide range of conditions. Once we are confined in the simulation result, we proceed to test on actual hardware maps in controlled lab environment at first. Finally, the first step is the fully implementation on the physical system for real-world test drives. The data from these real-world tests is invaluable if often revealed shortcoming in our model, which we then use to go back to the design phase and improve them. This continuous loop of design, simulation, testing, and implementation is fundamental to developing the robust and sophisticated autonomous system of the future. As we delve deeper into the mathematical model of MAV, we must first establish a clear and concise way to describe their motion, position, and orientation. This is accomplished by using a set of coordinate frames which are the subject of this slide. The importance of coordinate system cannot be overstated. They are absolutely essential for driving and understanding MAV dynamic behavior. Without a rigorous framework for defining where the drone is and how it is oriented, we simply cannot write the equation that governs its flight. Think it of this way: a drone's GPS might report its location in terms of latitude and longitude and Earth fixed frame, while its inertial accelerometer measures force received to the drone's own body. To make sense of both pieces of information, we need a mathematical way to relate these different points of view. To manage this complexity, we use several key coordinate frames. As the slide list, these include inertia, vehicle 1, vehicle, vehicle 2, body stability, and wind frames. Let's briefly touch on what some of these represents. The inertial frame or the earth frame is our fixed reference. You can think of it as being attached to the ground with axis pointing north, east, and down. This is the frame in which Newton's law of motion applied directly. The body frame is another critical one. It is fixed to the MAV itself, with the axis typically pointing out the front, the right wing, and the down through the bottom of the aircraft. The round sensor, like its gyroscope, make measurement in its frame, and the forces from the propellers are applied in the frame. The other frames, like the wind frame, are crucial for aerodynamics as they are aligned with the airflow over the vehicle, which is essential for calculating lift and drag. Each frame is chosen to simplify the description of particular physical force or measurement. Having multiple coordinate frame is only useful if we can translate information between them. This process is handled through mathematical transformation. Specifically, rotating matrices are used to convert coordinate between frames. The rotational matrix is a powerful tool that allows us to take vector description in one frame, say the force of the gravity in the inertial frame, and, and calculating its component in another frame, like the drone's body frame. This tells the autopilot how the force of gravity is affecting the drone's pitch and roll at specific. These transformations are fundamentally operational and that performs continuously by software running on the drone's flight controller, which represents here by the Arduino pilot board. The input, such as the data from the GPS module, are processed through these coordinate transformation to inform the control algorithm, which then generates the output to the motor. This constant conversation of information between the frame at the very heart of how MAE navigates its world. Now that we have established the need for coordinate frame, we need to practically way to describe the drone's orientation within those frames. This brings us to the most common method for representation an aircraft altitude, Euler's angle. This is a mathematical language we use to define how drone is tilting or pointing in space. Euler's angle consists of a set of three rotational roll, pitch, and yaw. Let's define these intuitively. The roll angle represents by pi, describing the rotation around the MAV's longitudinal axis, the line running from its nose to its tail. This is the motion would be seen as the wings back, left or right. The pitch angle theta is the rotation around lateral axis which runs from the tip to tip, wingtip to wingtip. This corresponds to the nose of the aircraft tilting up or down. Finally, yaw angle phi, psi uh, is the rotation around vertical axis causing the nose to turn left or right like a car steering. Together, these three roll, pitch, and yaw angle describe aircraft attitude relative to immediate field. Essentially, any possible rotation of the drone can be described by some combination of these three numbers. It is very important to note that the order in which you apply these three rotation matters. If you roll the drone first and then pitch it, and you will end up in a different orientation than if you had pitched it first and then rolled it. To ensure consistency, engineers and scientists agree on a specific convention. The common use rotational sequence for aircraft is child, theta, and phi sequence, which means that to define the final orientation, we start the aircraft level and pointing north. That then we apply the yaw rotation following the pitch rotation, and finally the roll rotation. This standardized sequence is crucial for ensuring that the control software correctly interprets the drawn altitude, while Euler's angle are intuitive and uh, widely used. They have one significant drawback known as the gimbal lock. The gimbal lock is a mathematical singularity that occurs when a drone reaches a pitch angle or of plus or minus degree, means its position straights up or straights down. At this precise orientation, the angle, the axis of roll and yaw becomes aligned, and as a result, they become indistinguishable from each other. This creates a mathematical problem where the drones effectively loses a degree of rotational freedom. The flight controller can no longer uniquely determine the aircraft's orientation, which can lead to instability and a complete loss of control. Well, this is not an issue for many standard flight operation. It is a critical consideration in high performance aerobic maneuver. This limitation is primary reason why more advanced system sometimes uses a more complex mathematical representation like quadration to avoid the problem of gimbal lock entirely. So far, we have discussed how to represent the MAV's orientation or altitude using Euler's angle. Now, we need to broaden our perspective to describe MAV's total motion through space. This is the domination of kinematics, which is the formal study of motion without considering the force and torque that causes it. The slides break down the full set of variable or state that we need to trace to have a complete picture of drone's movement at any given moment. For rigid body like MAV motion in three-dimensional space, there are total of 12 states that we must define. First, we need to know where the drone is in space. These are translation position states. We define the position using three coordinates. North represents as Pn, east represents as Pe, and down represents as Pd. These coordinates are all measured relative to inertial fluid. This means we have a fixed starting point on the ground, and we measure ground position as distance along these three axes from the origin. The northeast down or NED conversation is standard in aerospace and gives us an unambiguous global position for aircraft next. We need to describe how fast the aircraft is moving. These are its inertial velocities. Interestingly, we don't typically measure this in the fixed inertial field. Instead, we use body form components UVW. This velocity projected onto body axis. The variable u represents the forward force, v is the speed to the right, and w is the speed downwards, all from the drone's perspective. This is more intuitive for control because the thrust from the propeller, and the aerodynamic force are also guaranteed along these body axes. The next set of state should be familiar from our previous discussion. They define the drone's angular position. This is simply the drone's orientation in space, which we describe using Euler's angle, phi, g, and theta. As we cover these three angle representation, roll, pitch, and yaw of the aircraft, and together they give us a complete picture of its altitude. Finally, we just as we have linear velocity to describe how fast the drone is moving, we have angular velocity to describe how fast it is rotating. They are known as body rates, P, Q, R. These three variables describe the rotational motion of the MAVs. Specifically, P is the pitch rate or the how fast the drone is rotating around its forward axis. Q is the pitch rate or how quickly its nose is moving up or down. And R is the yaw rate, which is how fast it is turning left or right. These values are typically measured directly by the gyroscope on on board of the drone. Together, these tell state 3 for position and 3 for linear velocity, 3 for angular position, and 3 for angular velocity. Mhm. Gives us a complete kinematic description of the MAVs. The entire job of the flight controller is to understand and manage these 12 variations to achieve stable and controlled flight. Now that we have the language of kinematics to describe how MAVs move, we can advance to the next critical topic, dynamics. While kinematic answer how, uh, dynamics answers why. This is the study of the force and movement that cause the motion we observe. This is where we apply the fundamental laws of physics to create a model that can predict the MAV's behavior. In cornerstone of the dynamics is the Newton's second law. As the slide states, this law is applied to translation. F equal to mass into acceleration and rotation equal to m equal to j into omega, the degree of freedom. For translating motion, this is a similar concept that sums all the external forces acting on the drone is equal to its mass multiplied by its acceleration. These forces include gravity, the thrust from the propeller, and the aerodynamic forces like lift and drag. By summing these forces, we can determine how the drone will accelerate and move through space. Similarly, for rotational motion, the sum of all equal moments or torque is equal to the drone's inertial matrix multiplied by its angular acceleration. These moments, such as those generated by the different thrust of the propellers, are what causes the drone to roll, pitch, and yaw. The critical detail in applying these laws is the choice of reference frame. The Newton's law hold in internal frame. An inertial reference is one that is not acceleration. For our purpose, the fixed northeast drone frame we attach to the Earth's surface is considered an inertial frame. This means that all of our primary calculation for dynamic must have their motion reference to the fixed frame. This introduces a significant challenge because many of our forces and measurements occur in the drone's own body frame, which is constantly rotating to correct uh, to correctly apply In Newton's law, we must use the coordinate transformation we discussed earlier to translate everything back to the inertial frame, a process that adds mathematical complexity but is essential for accuracy. Focusing on the rotational dynamics, we encounter a key property of the airframe known as the inertia matrix, represented by J. In linear motion, mass is the single value that measures an object's position to acceleration. In rotation, the situation is more complex. The inertial matrix J is a concept that measures position to angular acceleration about body's axis. It is a matrix or a grid of numbers because an object's system to bring spun depend on its shape and how its mass is distributed relative to the axis of rotation. For example, a drone with a wide, flat body will be having hard to pitch or roll than S to R. The inertia matrix captures all of its geometrical information. This fundamental property of the drone's physical design is crucial for accurately modeling and controlling its rotational motion. The diagram you see on the slide illustrates the very focus and the moment acting on a single rotor that we must sum up and use in dynamic equation. After establishing the general framework of the rigid body dynamics, we can now begin to populate our equation of motion with the specific force and moment that act on the UAV. This slide focuses on the two most fundamental forces, gravity, which is constantly pulling the drone downward, and the force from the propulsion system, which counteracts gravity and allows for controlled flight. First, we'll consider gravitational force. This is the simplest force to model, but it is always represented, it always presents, and control system must constantly work to overcome it. The gravitational force, which can be denoted by F to the base g, and is the propulsion to mass and gravitational constant. This is simply the weight of the aircraft. A heavier drone requires more thrust to hover. This force also predicts in its direction as it is always acting in the downward direction relative to fixed inertial frame. While it is a simple vector, its component in the drone's body frame will change as the drone roll and pitch, and the flight controller must continuously account for it to maintain stability. Next, we have the force generated by the propulsion system, which for the multi-rotor MAV means the propellers. The primary force is the propeller's thrust, Fp. This is the lift force that generated by pressure difference created by the spinning airfoils of the propeller blades. For the purpose of control system design, this thrust is modeled as a function of throttling delta T and airspeed VA. The throttling system setting delta T is the command sent from the autopilot to the electronic speed controller, determining how fast the motor spins. The higher throttle results in more thrust. However, the air speed VA also plays a role. The efficiency of a propeller and the amount of thrust it produces can change depending on how fast the electron is already moving through the air. The sophisticated model will account for its effect. Of course, generating thrust isn't the only simple effect a spinning propeller has. According to Newton's third law, for every action there is an equal and opposite reaction. This leads to the creation of propeller torque mp. In order to spin a propeller, the motor must apply a torque to it. In reaction, the propellers apply an equal and opposite torque to the MAV ball. This reaction torque is what causes the body of the drone to want to spin. On quadcopter, this is cleverly managed by spinning two propellers clockwise and two counterclockwise, so its reaction torque cancels each other out during normal flight. Control other yaw is achieved by deliberately balancing these torque. It is important to note that this torque is proportional to the square of the propeller's angular velocity. This means that you you speed up a motor, the reaction torque increases as much as fast than the thrust does. This nonlinear relationship is the key characteristic that the flight control software must be designed to handle precisely. In addition to the force of gravity and the propulsion, we must also consider the force that are generated by MAVs interacting with the air itself. These are the aerodynamic force, and this slide focuses on two primary components, lift and drag. The origin of all aerodynamic force is the same. MAV movement, MAV's movement through air creates pressure distribution around the surfaces. As the aircraft's body, wing, and the propeller pushes their way through the air, they create variation in air pressure around them. The sum of these pressure differences result in a net force on the aircraft, which we can then break down into more useful components. The first component is lift, denoted by F lift. F lift is defined as the force perpendicular to the airflow. It is commonly misconception that lift always acts force, while it does counteracts weight in level flight. It is truly defined as based on the direction of the incoming air. For modeling purpose, this force is considered to act at a single point of the aircraft known as aerodynamic center. The second component is the drag or the F drag. F drag or the drag is the force parallel to the airflow, and it is acting in the direction that is opposite to the motion. As shown in the diagram, the drag is a resistive force that the Drawn's thrust must overcome to accelerate and maintain its forward speed. These forces are not constant. They change dramatically depends on how the MAV is flying. To predict these forces under different conditions, we use what we know as the aerodynamic coefficient. These are non-dimensional coefficients. For lift, drag, and pitch moment, we have CL, CD, and CL respectively. These captures the dynamic characteristics of aircraft shape. The great advantage of using these coefficients is that they remain consistently regardless of the aircraft size, speed, or the altitude at which it flies. The value of these coefficients are primarily influenced by the angle of attack, the angular rate, and the control surface. The angle of attack, which is the angle between the aircraft and the oncoming airflow, is the most significant factor in determining lift. The angular rate, how fast the MAV is pitching, rolling, or yawing, also alters the airflow and creates a damping force that can crucially be stabilized. Finally, on aircraft with control surface like the ailerons or the elevators deflects these surfaces intentionally, changes the aerodynamic coefficient to generate the moment needed to control the aircraft's altitude. By understanding how these factors influence the coefficient, we can create a comprehensive model that accurately predicts the aerodynamic forces on MAV in any phase of the flight. Just as the aerodynamic forces causes MAV to move, these also causes it to rotate. These rotational effects are called aerodynamic moment, and they are the key to control the aircraft's altitude. The slide explores these movements and the mechanism we use to manipulate them for controlled flight. We can divide the MAV's rotational behavior into two categories. The first, longitudinal dynamics, aerodynamics. This category deals with the moment causing motion in the pitch plane. The pitch plane is a vertical plane that cuts through the aircraft from nose to tail. The primarily pitching moment M is the task that causes the nose to pitch up or down. Managing this moment is fundamental to control the aircraft's speed and altitude. The second category is the lateral aerodynamics. This covers motion, all other motion, including the moment causing motion along the JB axis, which relates to side slip, and the crucial rotational motion is in the role capital I and YA, N, which is denoted by the letter Y. The rolling moment I causes the aircraft to back, and the yawing moment N causes its nose to swing from side to side. For many NAVs, especially fixed wing design, these controlling moments are generated by physical control surfaces. These are hinged flaps on wings and tail that the autopilot can move. The primary control surfaces are elevators, pitch control, and ailerons, roll control, and the rudder, yaw control. The fundamental principle at, at work is that the surface deflecting effect. When the control surface is deflected, it changes the shape of the aerofoil, which in turn leads to change in aerodynamic forces and moment. For example, deflecting the elevator up creates an downward force on the tail, causing a pitch moment that raises the nose of the aircraft. By precisely moving these surfaces, the autopilot can generate the exact movement needed to guide the aircraft. However, for multi-rotor MAVs, like the one shown in the diagram, control is achieved without these surfaces. Instead, the multi-rotor generates movement by precisely varying the thrust of their individual motor. As the diagram illustrates, the drone is subjected to a force of gravity F, uh, F gravity is equal to mass gravity acting at its center. To make the drone roll as indicated by the angle theta roll, the control system would increase the thrust from the motor on one side and decrease the thrust on the opposite side. This creates a net torque or moment uh, that the rolls the aircraft. The same principle applied for generating pitch and yaw moments. So whether it's through a subtle deflection of control surface or a rapid adjustment of motor speed, the core principle is same. We create controlled movement to change the MAV's altitude and directs direct its flight. To navigate the real world and compensate for factors like wind, a drone need to be able to sense its motion and its surrounding. This brings us to the topic of onboard sensor that makes this possible. As the slide states, the modern MAV rely on a suite of lightweight sensor to achieve autonomous flight capacities. The ability of a drone to fly with such stability and intelligence is not magic. It is a direct result of incredible sensor technology packed into their tiny airframes. The critical enabler behind this revolution are small, lightweight, and solid-state sensor using MEMS, micro electrical mechanical system technologies. MEMS are incredibly small devices that combines mechanical and electrical components on single silicon chip, much like a computer processor. This technology allows us to create sensors like the one picture on the slide, which are not only tiny and lightweight, but also power efficient and highly resistant to vibration. This is a miniaturization that truly enables MAV's autonomy, as it allows us to build sophisticated sensing system without adding prohibited weight or cost to the aircraft. A typical sensor suite on the MAV includes several components, each with a specific job. First, we have accelerometers, which measures specific force. These sensors are crucial for determining the orientation of the drone relative to the gravity. The next are the gyros, which measures the angular velocity. This is the data that tells the autopilot how fast the drone is rolling, pitching, and yawing, and it is absolutely essential for flight stability loop that keeps the drone in level. We also use pressure sensor to determine the altitude and airspeed. A barometric measurement which measures the air pressure to calculate the drone's height, while the pilot tube system can measure the dynamic pressure to find its speed through the air. To know which direction it is heading, the MAV uses magnetometer, which provides heading information by acting as a digital compass. Finally, to know this absolute location on the globe, the drone relies on GPS, which provides global positioning data. The ultimate purpose of gathering all this information is fed to the drone's brain. As the slide notes, these sensors provide essential data for guidance, navigation, and control system. The GNC system is the heart of the drone's autonomy. The navigation component uses the sensor data to figure out where the drone is and how it is oriented. The guidance component uses this information to determine the best path to waypoint or to accomplish the mission objective. And the control component takes the command from the guidance system and translate them into the precise motor action needed to fly the drone along the path. Every sensor in this suite plays an indispensable role in making this complex process possible. Now, let's begin our deep dive into the sensor suite by focusing on the first and one of the most important sensor on any MAVs, the accelerometer. The title of the slide is accelerometer, measuring specific force. These fundamental sensors that measure the specific force through proof mass displacement. To understand how they work, we look at their underlying principle of operation. As the diagram illustrates, an accelerometer can be a conceptual model as the proof mass responded by a spring. When the sensor casing accelerate, the internal mass due to its inertia tend to lag behind. This moment displaces the mass the proportion to accelerate. This tiny displacement is then measured electronically, often by detecting a change in capacitance between the moving mass and the fixed plate. This electronic signal is then converted into a measurement of acceleration. A crucial point to understand is what an accelerometer actually measures. It does not measure the total acceleration of the aircraft relative to the ground. Instead, accelerometer measure specific force F. The specific force is the difference between aircraft acceleration A and a gravitational acceleration G, which can be expressed by the equation F equal to A minus T. This critical this is a critical uh, distinction. For example, if a drone is sitting perfectly still on the ground, its aircraft acceleration A is zero. However, the accelerometer will not read zero. The gravity is pulling its spoof mass down, and the sensor measures the equal and opposite force from the internal spring folding up. Therefore, it will report an upward acceleration of 1 g. Conversely, if the drone were in free fall, both casing and proof mass would be accelerating downward at the same rate due to gravity. There would be no displacement, and the accelerometer would read zero. So specific force is non-gravitational force per unit mass if the acceleration that would be physically that you would feel free. Because of this physical principle, the real world output of an accelerometer is quite complex, which is why we need a detailed mathematical model to interpret its reading. The sensor output include linear acceleration, Coriolis acceleration, gravitational acceleration, and noise component. The linear acceleration is typically the value we are trying to determine, but we have to account for other terms also. Coriolis acceleration terms appear because the sensor is on rotating body. The gravitational term, as we discussed, is always present and is actually used for determining the drone's altitude relative downward. And finally, like any physical sensor, the output always includes random noise component that must be filtered out. Understanding this complex output is the first step towards using accelerometer data effectively in a navigation system. Continuing our content of MAV sensor system, we now turn to the rotational equivalency of accelerometer, the rate gyro. Rate gyros are essential for measuring rotational motion in MAVs, providing critical data for stabilization and control. If the acceleration tells the MAV which way is down, the rate gyro tells it how fast it spins. This high-speed feedback is absolute core of the autopilot ability to keep the aircraft stable, as it allows the system to instantly counteract any unwanted rotation caused by wind, gust, or other disturbances. While the diagram on this slide shows a classic mechanical gyroscope with a large spinning wheel, the operational principle of sensor in modern MAV is quite different and much more compact. The modern MEMS gyros use vibration spoof mass that experience Coriolis acceleration when subjected to angular motion. Inside the tiny MEMS chip, a microscopic mass is driven to vibrate back and forth at high frequency. When the drone rotates, the Coriolis effect exerts a force on this vibrating mass, pushing it in a direction perpendicular to its vibration. The sensor measures this way, this sideway displacement electronically, and the magnitude of that displacement is directly proportional to the rate of rotation. This clever design allows for the measurement of angular velocity, which no large, no larger a power-hungry spinning bar, making it perfect for small, lightweight MAVs. The specific measurement provided by this sensor are the drone's angular rate about its own body axis. This provides angular rates P, Q, R about the body axis. These three values correspond directly to the rotational velocity we defined in our kinematic model. Specifically, P is the roll axis, Q is the pitch rate along y-axis, and R is the yaw rate along z-axis. The flight control continuously monitor these three numbers, and if it detects non-zero value that wasn't commanded for the instant a roll caused by wind, it will immediately adjust the motor speed to create a counteract torque and drive that rate back to zero. However, like all real-world sensors, the rate gyro has their challenges. Its most significantly issue is that they are susceptible to bias drift. An ideal gyros could output a specific or perfect zero when stationary, but a real gyro has a small non-zero output called as a bias. This bias is not constant. It drifts slowly over time and is often temperature dependent. If we were to calculate the drone's angle by simply integrating these Rate measurement. This small drifting error would accumulate, leading to a large and even an increasing error in our altitude estimate. This is why the gyro requires careful calibration and periodic zeroing for accurate measurement. This is also the primary motivation for sensor fusion. When we combine the fast but drifty measurement from the gyros with a slow but stable orientation data from an accelerometer to get the to get the best of both the worlds. Our sensor overview now brings us to the class of sensor that measure property of the atmosphere itself, pressure sensor. These devices are not for measuring the force or rotation, but instead provides critical altitude and airspeed for MAV navigation and control system. Knowing the MAV's height and its speed relative to the air are fundamental requirements for safe and efficient flight. There are two primary types of pressure sensor used on MAV to accomplish this. The first is the absolute pressure sensor, which functions as the barometer or altimeter. This sensor simply measures the ambient atmospheric pressure. It is well-known principle that the atmospheric pressure decreases with altitude in a predictable way. The sensor leverages this relationship and is used to determine the height above the ground level, also known as HAGL, through the parametric formula. By measuring the local air pressure, the MAV autopilot can calculate its current altitude. This barometric altitude is often more stable and responsive to vertical changes than GPS altitude, makes it a critical input for tasks like terrain following and maintaining a constant height. Uh, the second type is the differential pressure sensor, which is most commonly implemented as pilot static system or pilot tube. This sensor is not measuring altitude but for determining airspeed. It measures dynamic pressure by comparing static and total pressure. As the diagram shows, the tube opening faces directly into the airflow to measure the total pressure, which is combined of the static ambient pressure and the dynamic pressure from the air's motion. A separate static port measures only the static pressure. The difference between these two readings gives you the dynamic pressure. This sensor is then used to calculate airspeed (VA) using Bernoulli's principle. The specific formula is VA is equal to 2Q divided by rho, where Q is the dynamic pressure and P is the air density. Measuring airspeed directly is vital, especially for fixed-wing MAVs, as it is the speed of air over the wings that generates lift, not the speed of aircraft over the ground. As with the other sensor we discussed, pressure sensors have their own source of error that we must account for in our model. This measurement are characterized by bias drift and Gaussian noise. The sensor bias can drift with change in temperature and its output will always contain a degree of random noise. For this reason, the sensor R requires calibration and filtering for accurate measurement. The raw pressure reading must be processed by the autopilot to remove noise and correct for bias before they can be reliably used by the guidance system, the navigation system, and the control system. This again highlights the importance of state estimation algorithm that we will cover shortly. To complete its understanding of this state, a MAV need a sensor of direction. This provided by direct compass, more formally known as the magnetometer. As the title suggests, their job is to provide a magnetic heading. These sensors detect Earth's magnetic field to provide heading information, which is essentially for the MAV's navigation. While GPS can tell a drone where it is, the magnetometer tells it is which way facing, allowing it to orient itself for a flight for the next waypoint. The underlying principle of magnetometer is quite straightforward. It utilizes Earth's three-dimensional magnetic field as a reference for dynamic for determining orientation relative to the magnetic north. The Earth itself generates a massive, uh, albeit weak magnetic field, and the sensor on the MAV is sensitive enough to detect it. By measuring the direction of local magnetic fields, the MAV can reliably determine its heading. The measurement process is handled by three-axis magnetometer aligned with the body axis. These sensors provide magnetic field strength measurement in all directions, which are used to calculate magnetic heading. However, using this using this measurement for navigation is not as simple as just pointing towards magnetic north. A significant complaint is that magnetic north varies with location, requiring compensation model like the World Magnetic Model (WMM) to convert between magnetic and true north. The direction of the magnetic North Pole is not the same as the direction of the geographical North Pole, and the difference between them, known as declination changes depends on where you are on the globe. Therefore, the MAV navigation software must use its current GPS position to look up the local declination from a model like WMM and apply a correction to get an accurate true north heading. Perhaps the biggest operational difficulty with magnetometer involves their challenge, because the Earth's magnetic field is so weak. These sensors are highly susceptible to uh, interference from nearby ferromagnetic material and electronic system. The steel screw in the drone's own frame, more significantly the strongest magnetic field generated by the current flow to the motor, can easily overwhelm the terrestrial field and give a false reading. This vulnerability is requiring a careful calibration and mounting. To mitigate this, the magnetometer are often mounted on masts as far from the power lines and motors as possible. Additionally, a rigorous calibration process is necessary where MAV is slowly rotated through all possible orientation to allow the software to build a map of drone's own magnetic field and learn to subtract it from the measurement. While the sensor we discussed so far are excellent at determining the MAV's orientation and its motion relative to the air, they can tell the drone where it is on the surface of the earth. For that, we rely on the Global Positioning System or GPS. GPS technology provides absolute position information, making it critical enabling technology for small UAVs. It is significant to modern drone operation cannot be overstated. GPS is what enables autonomous navigation, waypoint following, and return to home capability that fundamentals to MAV operation. This ability to create flight plan on map and have the drone execute it is a direct result of having reliable GPS receiver on board. The core principle behind GPS is the process called positional triangulation, an constellation of satellite orbiting the Earth is constantly broadcasting precise timing signal. The GPS receiver is in the MAV listen for these signal and measure the time it makes for them to arrive. By knowing the time, it can calculate its distance or a pseudo-orange from each satellite. The system requires at least 4 satellite pseudo-orange measurement to resolve this. Its full state. Three of these measurements are used to triangulate the receiver's 3D position, latitude, longitude, and altitude. The fourth measurement is needed to resolve for a critical variable, the receiver's clock offset. The timing requirement for GPS are so extreme that a small inaccuracy in the receiver's inexpensive quartz clock would lead to enormous positional error. The fourth satellite signal allows the receiver to constantly correct its own clock against the highly accurate atomic clock in the satellite, thus ensuring a precise positional lock. Of course, this process is not perfect, and there is a several source of measurement error. The total error budget is often referred to as the user equivalent range error or UERE, and it is the source included several factors. The first are the MRS data error, which includes which there are inaccurate in the satellite's reported position. The second are the satellite's receiver clock error. Despite the correction, a tiny residual timing error can be removed. Perhaps the most significant source of error are standard errors, which are ionospheric or uh, tropospheric delays. As the satellite radio signal travels through the Earth's atmosphere, it bends and slows down, which makes the calculation distance appear longer than it actually is. Advanced GPS system uses dual frequency receiver and augmentation system to model and correct for these errors. But for a typical MAV, it is important to understand that these environmental factors will always introduce some degree of uncertainty into the positional measurement. Beyond the inherent error source we just discussed, the accuracy of GPS measurement is highly dependent on several operational factors. As the slide indicates, GPS provide both positional and velocity data with accurate independent on satellite geometry and signal quality. A primary factor affecting accuracy is the concept known as dilution of precision or DOP. The geometric configuration of a satellite affects position accuracy. As the diagram on the slide illustrates, when the satellite, the receiver, is tracking all are clustered together in the sky, it results in a poor geometry or a high DOP value. This configuration, any small error in the timing measurement gets magnified or diluted into a large error in the calculated position. Conversely, when the satellite is spread wide across the sky, the geometry is strong, resulting in low TOP value and much more accurate positional fix. This geometrical error is broken down into several components, including HDOP, horizontal dilution of precision, and VDOP, vertical dilution of precision. For any pilot or autonomous system, the key takeaway is the lower TOP value indicates better accuracy. When we model the output of the GPS receiver for our control system, we need to understand the nature of the data it provides. The position model for typical GPS unit is discretizing time output, which is noise and slowly varying bias. This means it delivers positional update in distant packets, not as a continuous stream, and they up, and these updates are typically updated at 1 to 10 Hz. This is relatively slow update rate compared to the initial sensor, and the data is never perfectly clean. In addition to position, GPS also provide an excellent velocity measurement. Instead of simply calculating velocity by taking the difference between 2 points, modern receiver use a much elegant method, the velocity measurement, are derived from the Doppler shift of the satellite signal. As the MAV move, the frequency of the carrier wave from the satellite appears to change, and by measuring this change, the receiver can calculate this velocity very precisely. This carrier phase Doppler provides accurate ground speed (Vg) and course X measurement. In this fact, these velocity readings are often more reliable than differential position data. Attempting to calculate velocity by subtracting two noisy position uh, measurement would result in an even noisier and very unreliable velocity estimate. The Doppler method, by contrast, gives a smooth and accurate reading of the MAV's speed and direction over the ground.